Welcome to Dream Nest Stories. Tonight, we begin our journey deep into Earth's distant past, to a time before the world changed forever, when life flourished across lush continents and ancient ecosystems thrived unchallenged by cosmic catastrophe, a time that history calls the Cretaceous period. Long before the asteroid that would one day extinguish most of the dinosaurs crashed into our planet, the Earth was a place of astonishing biodiversity and dramatic environments, where animals great and small lived out their lives across warm forests, vast inland seas, and sprawling floodplains that stretched from pole to pole, creating a living tapestry of evolutionary wonder. Around 145 million years ago, this geological chapter began, marking the final period of the Mesozoic era and lasting until about 66 million years ago, making it the longest of all the periods in the Phanerozoic Eon. A vast span of time that saw continents split apart, seas rise and fall, and life diversify in extraordinary ways. In this late age of dinosaurs, the world was warmer than today's climate. There were no permanent ice caps at the poles, and tropical to subtropical climates extended into high latitudes, fostering dense forests rich with conifers, cycads, ferns, and the newly evolving flowering plants, known as angiosperms, which spread across the landscape and reshaped terrestrial ecosystems by providing new sources of food and habitat for a variety of life forms. The continents themselves were not yet in the positions we recognize now. They had drifted apart from the supercontinent Pangaea and were moving toward their modern arrangement. Oceans, shallow seas, and inland seaways covered large portions of low-lying land, slicing continents into islands and peninsulas that sustained unique, localized ecosystems. One of the most dramatic of these was the Western Interior Seaway that bisected North America from the Arctic Ocean to the Gulf of Mexico, creating an island continent known as Laramidia to the west and Appalachia to the east, each with its own distinct fauna of dinosaurs and other animals. Across these lands, dinosaurs reigned supreme as dominant terrestrial vertebrates, occupying nearly every ecological niche. Massive sauropods, the long-necked giants of the Cretaceous, roamed floodplains and forests, their towering necks reaching into the tree canopy to strip foliage, while horned ceratopsians like Triceratops grazed along riverbanks, and herds of duck-billed hadrosaurs fed in great numbers on low vegetation. Apex predators such as Tyrannosaurus rex stalked these lands as formidable hunters. Their powerful jaws and keen senses adapted to the challenges of a complex food web. In the shallow seas, marine reptiles including plesiosaurs and the agile mosasaurs ruled as apex predators of the oceans, while the skies were patrolled by flying reptiles called pterosaurs and the earliest birds. Ancestors of modern avians flitted among the branches. Life was rich and varied, and ecosystems were finely balanced. In the forests, insects such as beetles and early bees pollinated flowering plants, helping them spread across continents and leading to an explosion of floral diversity that supported herbivores and, in turn, the carnivores that fed upon them. Freshwater environments brimmed with fish amphibians, and small reptiles, while the oceans hosted abundant plankton, coral reefs, and a broad diversity of invertebrates whose life cycles help sustain the food webs of the seas. This bustling planetary system felt eternal and stable to its inhabitants, as though it had always been this way and would always remain so. Yet even in this age of abundance, change was already underway. While older theories once proposed that dinosaur diversity may have declined gradually before the end of the Cretaceous, driven by small shifts in climate and ecological pressures, more recent evidence paints a more nuanced picture. Fossils discovered in many regions, including high-precision datings from sites such as the Nashoi Beto member in New Mexico, suggest that diverse dinosaur communities persisted right up until the moment before the asteroid impact, showing a remarkable resilience and adaptability among species that had evolved over tens of millions of years. These thriving ecosystems, from the towering predators to the smallest forest dwellers, filled every corner of the land and represented the culmination of an evolutionary success story millions of years in the making. Beneath this spectacle of life, Earth itself was dynamic and alive. Continents continued their slow drift, mountains rose, seas shifted, and climatic patterns shifted over long cycles, creating a backdrop of slow but profound environmental change. Yet through all this flux, the planet hosted one of the most extraordinary chapters of life's history, a chapter in which dinosaurs were not relics of a fading past, but vibrant, successful, and dominant forms of life. It was a world teeming with motion, color, and sound. The call of predators echoed through wooded valleys, herds thundered across plains, and the distant waves of inland seas lapped against ancient shorelines under a sun that shone bright and warm. As you drift deeper into this story tonight, imagine walking through these ancient landscapes, feeling the warmth of the Cretaceous sun on your face, hearing the whisper of leaves in towering forests and the distant roar of giants that once ruled the earth. This was life before the fall, vivid, complex, and beautiful in its diversity, and it set the stage for the most dramatic transformation our planet has ever known, a transformation written in stone. And as that ancient sun slowly set over the thriving Cretaceous world, casting long shadows across forests, seas, and floodplains alive with movement, something far beyond Earth's horizon was already racing silently through the darkness of space, unnoticed by the creatures below, an object born from the earliest days of the solar system, traveling for millions of years through the asteroid belt between Mars and Jupiter, guided only by gravity and time, according to NASA planetary scientists. This rocky body was likely a carbon-rich asteroid approximately 10 to 15 kilometers wide, a remnant from the chaotic formation of the planets over 4.5 billion years ago. Its orbit gradually altered by gravitational interactions until it crossed Earth's path. With catastrophic precision, NASA solar system exploration, moving at an estimated speed of nearly 20 kilometers per second, faster than any natural process familiar to life on Earth, The asteroid entered Earth's atmosphere around 66 million years ago, compressing air ahead of it to temperatures hotter than the surface of the sun, long before it ever touched the ground. NASA Earth Observatory in a fraction of a second. The skies above what is now the Yucatan Peninsula blazed brighter than daylight, and the asteroid struck shallow coastal waters with a force equivalent to billions of Hiroshima-sized nuclear bombs, releasing more energy than any volcanic eruption or earthquake in Earth's known history. USGS: the impact instantly vaporized rock, water, and the asteroid itself, excavating a crater more than 180 kilometers wide, now known as the Chicxulub crater, buried beneath layers of sediment and revealed only through decades of geophysical research and drilling projects led by international teams including NASA and the European Space Agency. NASA JPL. Shockwaves rippled outward through Earth's crust, triggering massive earthquakes equivalent to magnitude 10 or higher, while molten debris was ejected high into the atmosphere and even into suborbital space, raining back down across the planet as incandescent fragments that ignited global wildfires. From North America to Asia, Smithsonian National Museum of Natural History. Tsunamis hundreds of meters high surged across ancient oceans, scouring coastlines and flooding inland seas, erasing entire ecosystems in moments and leaving behind chaotic sediment layers. Still visible in the geological record today, USGS. Yet the most devastating consequence of the impact was not the immediate destruction, but what followed in the sky above, as fine dust, soot from burning forests, sulfur aerosols from vaporized rock, and pulverized limestone were blasted into the stratosphere, forming a thick global veil that blocked sunlight for months to years. Nature climate models supported by NASA research indicate that surface temperatures plunged rapidly, photosynthesis nearly stopped, and Earth entered a prolonged impact winter, a sudden and severe cooling event that collapsed food chains across land and sea. NASA Goddard oceans acidified as sulfur compounds mixed with rainfall. Plankton populations crashed, and darkness spread even into shallow waters that once teemed with life. While on land, plants withered and herbivores starved, followed by the predators that depended on them. Smithsonian in less than a geological heartbeat. The world that had flourished for millions of years was transformed into a hostile, dimly lit planet struggling to sustain life, marking the boundary scientists call the Cretaceous-Paleogene extinction event, clearly preserved in rock layers around the globe by a thin band of iridium, a rare element on Earth but common in asteroids, serving as a silent signature of the moment the cosmos reached down and reshape the course of evolution. USGS as you drift deeper into rest. Imagine that quiet after the unimaginable force, a planet stunned into stillness, its once vibrant rhythms slowed beneath a darkened sky, where survival would soon depend not on size or strength, but on patience, adaptability, and time, preparing the way for life's most remarkable test. Beneath that dimmed sky, as ash continued to drift slowly toward the ground and the once bright rhythms of Earth fell into an unfamiliar stillness, the true aftermath of the asteroid impact began to unfold, not in moments or days, but across months, years, and centuries. As the planet entered one of the most severe biological crises in its history, a period scientists now describe as the Cretaceous-Paleogene mass extinction, with sunlight reduced by more than half according to climate simulations conducted by NASA and published in collaboration with atmospheric scientists. Photosynthesis nearly ceased across much of the planet, causing primary producers such as plants, algae, and phytoplankton to collapse at the base of the global food web. NASA Goddard Institute for Space Studies. Fossil evidence studied by the Smithsonian National Museum of Natural History shows that forests across North America, Europe, and Asia experienced widespread dieback, with leaf fossils indicating frost damage even in regions that had once been warm and tropical, confirming a rapid and dramatic drop in global temperatures. Smithsonian National Museum of Natural History. As vegetation vanished, herbivorous dinosaurs faced starvation, their massive bodies requiring constant intake of plant matter that no longer existed in sufficient quantity, and within a short geological span, many species disappeared entirely from the fossil record. Carnivorous dinosaurs soon followed, unable to survive without prey, marking the end of the great terrestrial reptile dynasties that had dominated Earth for more than 160 million years. USGS in the oceans. The darkness penetrated even shallow waters, disrupting plankton growth and triggering cascading extinctions among marine reptiles, ammonites, and many species of fish. While chemical analyses of sediment cores studied by nature reveal sharp increases in ocean acidity due to sulfur aerosols dissolving into rainfall, further stressing marine ecosystems already weakened by the loss of sunlight. Nature, yet amid this widespread destruction, life did not vanish entirely, and the fossil record reveals a crucial pattern. Survival favored the small, the adaptable, and the sheltered. Burrowing animals, such as early mammals, found refuge underground where temperatures were more stable and food sources like seeds, roots, and detritus remained accessible, while freshwater species such as turtles, crocodilians, and amphibians endured by slowing their metabolisms and surviving on minimal energy in rivers and lakes less affected by oceanic collapse. Smithsonian birds, the only living descendants of dinosaurs, survived likely due to a combination of small body size, flight capability, and flexible diets, as supported by fossil discoveries and comparative anatomical studies published in Nature, which show that avian lineages capable of seed consumption and rapid reproduction were more likely to persist through the long darkness. Nature insects, though often overlooked, played a critical role in Earth's recovery, with fossilized pollen and spores analyzed by USGS researchers indicating that, while many insect populations declined, enough survived to later pollinate the first wave of post-extinction plant life, helping ecosystems slowly rebuild from the ground up. USGS over an estimated span of tens of thousands of years, the dust veil gradually thinned. Sunlight began to return, and temperatures stabilized. But the world that emerged was forever changed, quieter, emptier, and open to new evolutionary possibilities. As nearly 75% of all species had vanished, leaving behind ecological space waiting to be filled. As you sink deeper into rest, imagine that fragile persistence of life during Earth's darkest hours. A silent endurance unfolding beneath cold skies, reminding us that even in moments of profound loss, survival is written not in strength alone, but in adaptability, patience, and the quiet passage of time. As the long impact winter slowly loosened its grip on the planet and the dense veil of dust and aerosols thinned in the upper atmosphere, faint sunlight once again began to reach Earth's surface, initiating a fragile and uneven recovery that unfolded not in years, but across tens of thousands of years, marking the quiet beginning of a new biological chapter. Geological evidence examined by USGS researchers shows that the earliest sign of terrestrial recovery appears in sediment layers, immediately above the Cretaceous-Paleogene boundary, where pollen grains of flowering plants vanish almost completely and are replaced by an overwhelming abundance of fern spores, a phenomenon known as the fern spike, observed on every continent and widely accepted by paleobotanists as proof that hardy, fast-growing plants were the first to recolonize devastated landscapes. Ferns, which reproduce via spores rather than seeds, thrive in disturbed environments and require minimal soil nutrients, allowing them to spread rapidly across ash-covered ground where forests once stood, stabilizing soil and preventing erosion while creating the first foundation for ecosystem renewal. A process documented extensively by the Smithsonian National Museum of Natural History through fossil pollen analysis. As plant life cautiously returned, atmospheric carbon dioxide levels gradually stabilized, and temperatures began to rise from their post-impact lows, though the climate remained volatile, with rapid swings between cold snaps and warmer intervals. According to climate models developed by NASA Goddard researchers, studying impact-induced climate perturbations in the oceans, recovery followed a similar pattern of slow resilience, as microscopic phytoplankton species capable of surviving low-light conditions began to repopulate surface waters, restoring the base of marine food webs, while sediment cores analyzed in nature revealed that carbonate production slowly resumed, signaling the return of ocean chemistry toward equilibrium after extreme acidification. On land, the absence of large herbivorous dinosaurs created ecological space that had not existed for over 160 million years, allowing surviving vertebrates to explore new niches without competition from massive reptiles. And fossil assemblages indicate a gradual increase in small mammal diversity during this interval, though most remained no larger than modern rodents. Insects also rebounded alongside plants, with beetles and early pollinators playing a critical role in spreading vegetation, accelerating recovery in a feedback loop that slowly increased biodiversity. Rivers and freshwater systems became vital refuges during this phase, supporting amphibians, fish, turtles, and crocodilians that had survived the extinction and now expanded into newly available habitats, while birds diversified rapidly, filling aerial niches once occupied by pterosaurs, as shown by fossil wing morphology studies published in Nature. Despite this progress, recovery was uneven and fragile, with repeated environmental stresses delaying full ecosystem stability for hundreds of thousands of years, reminding us that planetary healing is a slow and patient process, rather than a sudden return to abundance. As you rest with this image, imagine the Earth breathing again for the first time after catastrophe. Green slowly returning to gray. Life cautiously testing the sunlight. One spore, one leaf, one quiet heartbeat at a time. As ecosystems stabilized and plant diversity increased, evolution began to move in new directions. And over the next several million years, mammals once small, nocturnal survivors hiding in the shadows of dinosaurs began a slow but profound expansion that would forever reshape life on Earth. Fossil records analyzed by Smithsonian paleontologists reveal that early Paleogene mammals rapidly diversified in form and function, evolving specialized teeth for different diets, stronger limbs for running and climbing, and increasingly complex brains that enhanced learning and adaptability, traits that proved advantageous in a dynamic post-extinction world. Without large reptilian competitors, mammals expanded into herbivorous, carnivorous, omnivorous, arboreal, aquatic, and burrowing roles, exploiting ecological opportunities left vacant by extinct species. While Nature published phylogenetic studies show a burst of mammalian lineages emerging within just a few million years of the extinction event, climate during this time gradually warmed, reaching a greenhouse state known as the Paleocene thermal maximum, documented by NASA climate reconstructions, which further influenced mammalian evolution by promoting forest expansion and enabling species to spread across continents via land bridges, such as the Bering connection between Asia and North America. Whales evolved from land-dwelling ancestors returning to the sea. Bats took to the air using powered flight, and primates adapted to life in trees, developing grasping hands and forward-facing eyes, traits critical for future human evolution. Birds also continued to diversify alongside mammals, becoming dominant aerial vertebrates, while flowering plants co-evolved with insects and herbivores, creating complex, interdependent ecosystems resembling modern environments. Oceans recovered their full productivity, with coral reefs reestablishing and fish diversity increasing, though the marine world remained forever changed by the loss of ancient reptilian rulers. This period demonstrates a central lesson supported by evolutionary biology research. Mass extinctions do not simply erase life. They reorganize it, clearing evolutionary pathways that allow new forms to flourish, a process repeatedly observed throughout Earth's history and documented by USGS stratigraphic studies. As you drift deeper into rest, consider how your own existence traces back to these quiet mammalian pioneers, small creatures who survived darkness and emerged into a world of possibility, shaping a lineage that would one day look back and understand its origins written in stone today, tens of millions of years later. The story of the dinosaur extinction and life's recovery remains etched into Earth itself, preserved in rocks, fossils, and planetary scars that quietly remind us of our place in a vast and dynamic universe. The Chicxulub crater, buried beneath the Yucatan Peninsula and studied through drilling projects supported by NASA and international research teams, stands as a physical record of the moment Earth's trajectory changed. While the thin iridium-rich layer found globally at the extinction boundary continues to serve as chemical evidence linking the catastrophe to an extraterrestrial impact, as confirmed by USGS and Nature Studies. Yet this story is not one of destruction alone, but of continuity and resilience, as every bird that sings today, every mammal that walks, swims, or flies, descends from survivors that endured one of the most extreme challenges life has ever faced. Modern space agencies now track near-Earth objects precisely because this ancient event demonstrated the power of cosmic forces to influence biological destiny, leading NASA to establish planetary defense initiatives designed to detect and potentially deflect future threats. From a broader perspective, the extinction reminds us that evolution is shaped not only by slow adaptation, but by sudden, transformative events that reset ecological systems and open new evolutionary pathways. Humans, born from the mammalian radiation that followed the extinction, carry this cosmic legacy within their DNA, a reminder that intelligence, culture, and curiosity emerged from resilience rather than dominance. As you settle into sleep, imagine Earth floating quietly through space beneath the same stars that once watched dinosaurs fade and mammals rise. A living planet shaped by catastrophe yet defined by survival, endlessly adapting beneath the silent rhythms of the universe, where even endings become beginnings and life, against all odds, continues.